Hey everyone, office hours today. We got a couple questions starting with prep activity, limiting reactants prep activity number 11. This is a kind of long one. This is after you've done a couple limiting reactants activities, you got to do it backwards. So it says, one less question, this time try it backwards. We're given the products and need to think about how we can use that to get the amount of reactants. So we have an unknown mixture of ethane gas and oxygen. So our mixture is going to be ethane gas. First thing we have to know is what is ethane gas? Methyl ethyl, so that should be C2H6 gas plus O2 gas is going to go to, if we assume perfect combustion, CO2 gas plus H2O gas. Of course, we've got to balance our chemical reaction as well. Sorry, I'm doing it in my head. So I knew I wanted to get an even number of oxygens. So I knew I needed an even number in front of this. So I was like 6, I'm going to put a 2 there. So I've got 12 hydrogens, 4 carbons, 4 carbons. That's going to be 6 plus 8. I should be up 12. So that's going to be 6 oxygens there. Right? 3 plus 4, nope, 7. Math is bad. 6 plus 8 is not 12. I tell you, the things I seem to have the most trouble with during office hours is simple addition. Okay, so this is what we've got. We're given our unknown mixture. And Mia, where did you get stuck with on this problem? That was a weird sentence.
I didn't even set it up. I was confused
okay.
on the whole thing. So.
You confused on the whole thing. So typically, did you watch my stoichiometry video? Stoichiometry problem solving?
I'm pretty sure I did.
Okay. So what we mostly see in our problems is, I like to think about it as what we start with, how the reaction proceeds, and then what we've got at the end of the reaction. And I like to do my math in this kind of like column way. And what we usually do is we start with some amount of reactants, and then those become some products. Now, the thing that's interesting about this is because of the conservation of material, right? Because if this is a closed system, all of our hydrogen is already trapped inside here. We could take the amount of water that's produced and figure out how much C2H6 there must have been. We can take the amount of carbon dioxide produced and figure out the amount of carbon from the C2H6 there must have been. So we can actually do this backwards, not knowing what we started with, but knowing what we ended up with. So this says at the end of an unknown mixture, when we know the total mass of this mixture, we get 1.86 grams of water, we know we get that, and we know we start with these two things put together as 7.79 grams of mixture. And it says we know a couple other things, right? It says, and this is really important. So the key here is the problem reading abilities. The problem with number 3 on master question 13 should be fixed now, by the way. I think. If you refresh your page. Okay, back to this. So let's read this really carefully. We are given 7.79 grams of an unknown mixture of ethane gas and oxygen. We burn it in a sealed container. We get water, carbon dioxide, and ethane gas afterwards. So that sentence is actually telling us that there is excess here. So this is telling us that the oxygen must be running out, and there must be some amount of ethane gas, some amount here, and some amount of H2O. Now that doesn't, right off the bat, seem like enough information. But notice what we can do is we can say 18 grams of H2O, oh sorry, 1.86 grams, convenient, 1.86 grams H2O times 1 mole H2O has 18 grams of H2O. That is going to give us the number of moles of H2O we must have. Calculator. 1.86 divided by 18. 0.1033 moles H2O. Now here's why that is important. In the conceptual thinking, and I'm assuming that you were able to get through all of the other problems.
Yes.
So you kind of have a good sense of doing stoichiometry forwards. So what we know, and I'm going to switch this number to the number of moles because that's how I think about it. What we know about this moles of H2O is that the amount that was made. Also, are you comfortable with my column addition method?
Yeah, that makes sense.
Okay, so we know we started with 0 H2O because it was all ethane and oxygen. And we know during the reaction, that amount of H2O was produced based off of some mole ratio with whichever thing was limited. Since we're told that the ethane gas is in excess, there's some left over, we know that this number of moles of water produced has to be related to the amount of oxygen that was produced, and it has to be related to the amount of CO2 that's going to be produced. Right? So we can use this moles of H2O to figure out how many moles of limiting we must have had. So since I know that the O2 is the limiting reactant, right? This is kind of the trouble with doing it backwards, is we have to flip all of the thinking we've done previously. So I can say 0.1033 moles H2O times 7 moles O2 per 6 moles H2O. I know that if I take this moles of H2O and I multiply by the mole ratio, that's going to give me my moles of O2 gas, because we know the moles of O2 gas is limiting. And once we've got the moles of O2 gas, the whole problem starts to unravel really a lot easier than it first looked like. But it was this first kind of logical step of how do you take this moles of H2O, figure out what's limiting, figure out how much of your limiting reactant you had. Because now we can take this moles of O2 gas, convert it to grams of O2 gas, and figure out the starting grams of each of these. Does that make sense? We're still going to do it together, but I just want to make sure you're following the logic so far.
Yeah, the logic makes sense.
Okay, so let's go ahead and do that together. We're going to take our 0.1033 times, that's good, times 7 divided by 6, and, whoa, I made a mistake. 0.1033 times 7 divided by 6. That's going to give me 0.1205 moles of O2 gas, which multiplied by the molecular weight of O2 is going to be 3.85 grams O2 gas. Because of the relationship between the products and the limiting reactant, I can figure out how much O2 gas I must have had. Now we can start putting this information in, and we can turn it back into our familiar forward stoichiometry problems. So I'm going to go ahead and write 3.85 grams here, figured out from the calculation there. I'm going to take my mass of total sample and subtract the 3.85 off, so I'm going to have 7.79 minus 3.85, and that's going to give me 3.93 grams here. I can then, after I have those two numbers, technically we don't have to do this like a forward stoichiometry problem, but after we have those two numbers, now we can just do it like the rest of our typical problems and make sense of the stoichiometry after we've got that starting amount. It really depends on our understanding of how the product relates to the limiting reactant. So we know, let's see, I'm going to leave this 0.1033, 0.1205 minus 0.1205 plus 0.1205 times 4 to 7 plus 0.1205 times 6 to 7. And if I did everything correctly, 0.1205 times 6 to 7 will give us this number, right? 0 plus this gives us that. And then I can also do minus 0.1205 times 2 to 7. And if this is a lot for those of you who haven't watched my stoichiometry video, I'm doing a lot of quick math here. Not only to make sure I've got it conceptually correct, but also just because once we practice these, we can do them pretty quick. Calculator. 0.1205. The first thing I'm going to do is check to make sure I get that number back, that I didn't make any mistakes. 0.1205 times 6 divided by 7. Looks good. A little bit of a rounding error. I probably could have kept a couple extra digits, but close enough. We're within 0.1% of it. Then I could do 0.1205 times 4 divided by 7. And that's going to get me my amount of CO2 produced, 0.0689 moles CO2. I think it asks for these answers in grams, not moles. Yeah, it asks for it in grams, so you're going to have to multiply these by molecular weight, but that step's easy for us at this point. We end up with 0 here because limiting reactant should end up with a 0. And then I've got one more step to do here. 12, 24, 30, 3.93 divided by 30, 0.131 minus 0.1205 times 2 divided by, nope, that's not going to work. 0.12. Got to be careful with the calculators in the parentheses, otherwise everything goes bad. 0.1205 times 2 divided by 7, negative plus 0.131, 0.09657. And that's how we do stoichiometry backwards. This again is the core step here, is recognizing how the moles of product relate to the moles of the limiting reactant. And after we get that, we can kind of pull the puzzle apart piece by piece. You'll notice the limiting reactant really becomes the thing that's the most important information in the problem. Which is the limiting reactant and how much of the limiting reactant there is going to tell us everything about how much products we make and how much excess reactant we have. So figuring that out was kind of the key part to this problem. Good?
Yeah, the only question I have is where did you get, I don't know if I missed a step, the 3.93 grams of the ethane?
Oh, so after I got my moles and grams of O2, I did my original mass of total ethane and oxygen together before the reaction, and just did 7.79 minus 3.85.
Okay, I have a different number, so I think maybe that was why.
Oh, that could be why. Yeah, so I did starting mass minus my oxygen gas mass.
Got it.
Weird phrase.
Thank you.
You bet. And yes, we can do a limiting reactant report. George, that is actually the next question we're doing. Let's see here. Limiting reactant report. This one is confusing people for a couple of reasons. One, because they didn't watch my video. Two, because LabPal is self-referential and it believes what you say. So if you tell it the wrong thing, it will then run with that wrong thing and start giving you kind of wrong results. The place where most people have had trouble with this is they're not entering their total mass of unknown mixture used correctly, or they're not entering their mass of filter paper plus precipitate correctly. If you have a mistake in any of that data entry, LabPal will continue that mistake through the entire problem. So the most important thing to do for this is to make sure that you've got those things entered incorrectly. Because if you don't, LabPal will be sad and confused. And it just believes you. Computers don't know how to not believe you. It'll just believe you. So let's go ahead and look at this. Again, I might have different numbers than you, but there's this large block of text. And I'm going to write down the numbers. You obtain a 0.844 gram unknown sample. I had sample A. I transferred it to a 50 ml beaker, placed a magnetic stir bar in, added water, and stirred it. Then I collected my solid. My filter paper weighed 0.651 grams. That's because it's too hard to scrape the solid off the filter paper. I set it out, I let it dry, and I get 0.967 grams of filter paper plus precipitate. And that's pretty much all the data we have. So then the question becomes, well, what do we do with this? We put in our unknown mixture sample ID. For mine, it's A. Put in our total mass, 0.844 for me. You'll have some range of possibilities. The biggest mistake I've seen is people just put 1 gram there, and then it's different than what LabPal thinks you have, and that just throws everything off. So LabPal trusts that you're putting the right number in there. Massive filter paper, again, LabPal's going to trust you put the right number in there. Massive filter paper plus precipitate, again, so there's those 3 spots that LabPal's going to trust that you put in the thing that it's expecting from you. And if you mess up any of those, then it starts having some self-referential issues. Then to get the mass of precipitate, we're just going to do the mass of filter paper with precipitate minus the mass of filter paper. 0.651 minus math, order of operations matters. 0.967 minus 0.651. And I'm going to get 0.316 grams. The other part that's really important here is when we go to moles of precipitate, we have to use the correct molar mass. And this is a really subtle thing that's in the procedure. Where is it? I just realized this might have a piece of information that you don't know about. So we have copper phosphate as our oh no, it's right there. Okay. So you'll notice that in the unbalanced chemical reaction, it gives you copper phosphate trihydrate. The other place where people make a mistake is they use, to get to the moles of precipitate formed, they use the wrong molar mass. And this is a very interesting kind of particular experimental thing, a real world thing. Right, when we do our stoichiometry, when we're doing stuff on the board, we assume that everything is perfectly dry. But if you've ever lived someplace with high humidity, you know that your sugar kind of soaks some water out of the air. Your salt will soak water out of the air and get kind of like chunky. And that's because there's some natural amount of water in the air around us, and different materials will absorb certain amounts of that water. The only way to make sure that you don't have that water when you're actually doing your samples, when you're doing this type of experimentation, is we would have to take our sample and put it in an oven at 103 degrees Celsius for 8 hours to drive all the water out of our crystal structure and have perfectly dried copper phosphate. Since we didn't do that step, because who's got time for that, you have to make sure you use the copper phosphate trihydrate molecular weight of 434.63. So that's another place where people make a mistake. After we get that, the moles of precipitate, then there's some kind of logical thinking, and then our mass percents. So let me double check before I start running forward too much more. Kyle, did that kind of answer your question about the moles of precipitate?
Yeah, I think I did that and I got the wrong answer, but I'm going to try it again and see if something changes.
Yeah, so double check that you entered in your numbers correctly from what it thinks you should have, and make sure you're using that copper phosphate trihydrate molecular weight. That's probably the most common mistake people make, is they just use the copper phosphate molecular weight. The 0.316 grams, that was my, assuming I didn't make a math mistake, that was my filter paper with precipitate on it, minus the weight of my filter paper, so I could get the weight of my precipitate alone. And George, did that answer your question as well? I'm not sure where your question was.
I was fine on that stuff. I'm a little confused on finding the mass of the limiting reactant and excess.
Okay, so this kind of goes back to what we just did with limiting reactant prep 11, right? We can find, were you able to identify your limiting reactant correctly? You're muted.
Copper chloride.
Okay, so looking at our chemical reaction here, we've got copper chloride plus sodium phosphate, dodecahydrate. No one actually says dodeca, they just say hydrate. Goes to sodium chloride plus copper phosphate hydrate. Right, and in this same way, where we've got our start reaction and our end. So at this point, if we've got the moles of product made, we can do that same kind of logic we did in the previous problem, where the moles of product made has to be related to the moles of our limiting reactant, whichever one the limiting reactant is. So I know the moles of my product made must be related to my moles of limiting reactant, because that's going to be what controls how often the reaction can happen. After I've got my moles of the limiting reactant, I can find my grams of limiting reactant, and then I can just do my starting unknown minus that grams to get the grams of my excess component. Let's do it together. Now that we've got that logical kind of thinking together, let's do it together. First things first, balanced chemical equation. This should be CuCl2. Yep, that should be CuCl2. We don't need the parentheses there. I'm getting carried away. Copper, we're going to need a 3 there. Sodiums, phosphates, we're going to need a 2 there. We're going to need a 6 here. And you might be thinking, hey, what happened to all of those waters? There should be 24 waters and we only have 3. Remember that this is aqueous, so there's just extra water floating around. We don't need to balance those hydrates. They're just important for the molar masses. I had 0.316 grams of my product made. And I'm going to just do the same type of logic we did last time. 0.316 grams I'm going to multiply by the molecular weight, which is, inverse of the molecular weight, which is 1 mole, has 434.6 grams. This will get rid of the grams of copper phosphate trihydrate and just give me the moles, which I can already tell is going to be a small number. I'm going to switch it to scientific notation. It's so small. 7.27 times 10 to the minus 4 moles copper phosphate trihydrate. Right, now once I have those moles, I'm like, well, great, what does that get me? We have to remember that the moles produced here, I didn't start with any copper phosphate. So the amount that's added here is going to be directly related to the limiting reactant, the amount that I'm subtracting over here. So I can do my question mark. I can essentially say, since we know copper chloride is the limiting reactant, I know that my copper phosphate is going to be the moles copper chloride times the mole ratio, which is a 1 to 3 mole ratio. Right, and I get this kind of logical statement where I know it has to be, and we could write it down. I just came up with a nice, I've been trying to think of a nice mathematical way to write this down for like the last 15 minutes, and I just found it. So for our product, when we've got a known product, we're essentially going to end up with this equation of 0 moles. I always like to start with 0 because it's important for the future. Plus moles limiting reactant times mole ratio equals moles product. Right? This is kind of the essential idea for our stoichiometry. We always start with 0 product in this class. In the future, we'll start with non-zero there. But it's this idea of my moles of limiting reactant times the mole ratio is equal to my moles of product. So if I've got my moles of product and I know what my limiting reactant is in terms of identity, then I can get this mole ratio. And now I've only got one thing that I need to solve for, that moles of limiting reactant. So I'm going to do moles of product divided by this mole ratio. So I'm going to do this moles of product times 3 over 1. And that will get me my moles of copper chloride. Does that sound good?
So I just divide what we just calculated by 3, or what I calculated. I guess I had the numbers, but I divide the number of moles of copper phosphate hydrate by 3.
Well, follow through with your mole ratio. So write down this equation for your problem.
Okay.
Make sure you know where the mole ratio is, which mole ratio you have, because the difference between multiply and divide is really crucial here.
And then the mole ratio is 1 to 3.
Why?
because there's 3 coefficients for copper chloride's 3 and the coefficient for copper phosphate.
Perfect. Right, so our molar ratio is 1 to 3.
So you multiply by 1.
Well, the multiply is on this side. What's our unknown, though?
The product?
No, we've got our moles of product. The copper phosphate trihydrates are moles of product known.
Oh, yeah. Okay. Yeah, okay. Yeah, I wrote it in wrong.
Yeah, well, that's okay. I mean, these two problems, the limiting reactant prep 11 and this last part of the report form, these are both stoichiometry backwards. So if you haven't been practicing it, and when I say practicing it forward, I don't just mean getting the right answers. I mean thinking through the logic of how these problems work, right? These problems are always kind of the same steps. There's always the same connectivity between them. If you didn't realize this connection between limiting reactant and products in like a really fundamental way, it's really hard to think through them backwards as well. That's part of why we like doing problems backwards. It challenges us from doing what we call algorithmic learning, where you just like, give me numbers, I can crunch it through like a computer, versus actually having to think through an analytical problem. So I'm gonna let you work on that. After we've got this moles of copper chloride, that gets us grams of copper chloride, we can use that to find grams of sodium phosphate, and from there it should all like tumble out pretty easily. Just like we did for prep 11. Any other questions about this one before I move on?
Is that from the results section or is that from the data section?
That's the results section.
Oh, okay. So the moles that we got for the precipitate, we could plug that into the first part, but then the rest of it is
the backwards thinking. So it's, yeah, so that's your moles of precipitate is just your measured moles of precipitate, nothing tricky there. It's when you start trying to figure out your mass of limiting reactant, your mass of excess reactant, that it's the backwards thinking.
Yeah, so you would use your 7.27 as your moles of precipitate and then use that to, yeah, okay.
Yes, to think backwards.
Thank you.
Perfect. Are we ready to move on? Okay. Let's see. Carbonates question 2. Okay, this is actually a very interesting problem. It was actually a problem on the mastery questions last week as well. So if this problem feels really familiar, you're right, it should be really familiar. If the slight changing in wording made you think that this was a completely different problem you've never seen, again, look for those patterns. Look past the words to the chemistry that's going on. A lot of students get caught up on trying to read the problems and not thinking about the chemistry that's going on. So let's go ahead and read this and see what's going on. A 1.268 gram sample of metal carbonate was treated with 100 milliliters of 0.1083 molar sulfuric acid, yielding CO2 gas in an aqueous solution of metal sulfate. The solution was boiled to remove the dissolved CO2 and then was titrated with sodium hydroxide. A 7.12 milliliter volume of sodium hydroxide was required to neutralize the excess sulfuric acid. What's the identity of the metal? There's a couple. So the first thing you should be doing as you read through the problem is identifying the explicit information, the implicit information, and the connectivity between them. We got our sample, we've got moles of sulfuric acid, we got moles of sodium hydroxide, and a really important thing to realize here is in our grams of sample, we're told that that first reaction has excess sulfuric acid. The very last phrase there, to neutralize the excess sulfuric acid, is actually really important. So when we look at this, we can kind of think about this in terms of the sulfuric acid is the thing that's going to be reacting twice. It's going to react with the carbonate, and it's going to react with the sodium hydroxide. And I'm going to do this kind of in backwards from the way it's written, just because I think the math will look a little prettier. So I'm going to have H2SO4 plus 2 NaOH goes to, sorry, I forgot my states of matter, never forget your states of matter, goes to Na2SO4 aqueous plus 2 H2O liquid. Right, so this is the second reaction that's going to happen where the excess sulfuric acid is reacting with sodium hydroxide to produce some amount. The first reaction that's happening is our unknown metal carbonate is going to go to make, that's a weird S. That's not much less of a weird. The metal sulfate plus CO2 plus H2O. Right? And this is the first reaction that happens where the metal carbonate reacts with the sulfuric acid. And you could be thinking, hold on, what if it's X2? Well, then it's just going to be X2. This will change our thinking at the end, but in terms of balancing our chemical reaction, it's not going to change the balancing of our chemical reaction. So I'm just going to leave it as X1 for now. The most important thinking here is the fact that we've got sulfuric acid reacting twice. So my moles of sulfuric acid is going to be equal to the moles reacting with sodium hydroxide plus the moles reacting with the carbonate. So this is kind of what's going on in terms of our thinking. I know the sulfuric acid reacts with the carbonate, and we get some excess sulfuric acid left over, and then we perfectly neutralize it with the sodium hydroxide. So we're going to use up all of our sulfuric acid by reacting with these two things. And now the question becomes, well, how do we figure out how much of these two things we have? The sulfuric acid one is a little bit easier to do because it's a 1-to-1 ratio. So I'm just going to go ahead and say my moles of sulfuric acid would be equal to my grams, 1.268 grams, times 1 over molecular weight, times my 1-to-1 mole ratio. I don't know my molecular weight though, so in writing the equation down like this, that's what we're trying to solve for. My moles of H2SO4 reacted with sodium hydroxide. This one we know all the values, but we've got to make sure we don't forget the 2-to-1 ratio. It's 71.02 milliliters. This is for my given values, 71.20 milliliters. I'm going to go ahead and convert that to 7102 liters. That's too small to see. Let me give myself a little bit more space. 0.0712 liters times the molarity, which is 0.1241 molarity. And I also have to remember for this one, my moles of H2SO4 reacted with sodium hydroxide is going to be 1 mole of H2SO4 for every 2 moles of sodium hydroxide. If you're not careful with your units, it's really easy to get that flipped over, but because I have everything in terms of H2SO4, I'm going to want the coefficient of H2SO4 on top, and the coefficient of the other thing on bottom. This is going to be equal to the total amount of H2SO4 we used, which we also are given. That's 0.1 times 0.1083. And you'll notice, after we do our thinking about the chemical reactions and which thing is kind of what I call our bridging reactant, that is to say the thing that's reacting twice. I know sulfuric acid has to react with sodium hydroxide and metal carbonate, and plugging in all of my known values, the only thing I have left to solve for is the molecular weight. So now it's just doing some rearrangement. 0.01083 minus, don't forget your factor of 1/2. That's the most common mistake people make in this problem, is they forget that these two things have different mole ratios. They just plug 1 to 1 in for both of them, and that creates a huge headache. 0.07121 times 0.1241. That divided by 2 equals minus 0.00449 is equal to 1.268 divided by molecular weight. And then I'm going to solve for molecular weight. I'll bring my molecular weight over, bring that down. Again, your numbers are probably different than mine, but we'll see how this goes. Negative. And I get a molecular weight equal to 197.7 grams per mole. Taking this amount of grams, dividing by that amount of moles of just the carbonate reacted should give me my molecular weight. This does not tell us which metal it is yet. So in order to get at just the metal, I'm going to subtract off the molecular weight of carbonate, which I'll do this logical step. So this is solving perfectly fine for the stoichiometry, but we want the identity of the metal. So I'm going to do 197.7 minus 60. I've got the kind of logic there. That's going to give me 137.7 for my mass of my unknown metal. At this point, we get our periodic table, and we've really got two options. It could be something from the alkali metals, but 2 of them. So if I take this, divide by 2, see if it's close to anything. Or it could be one of my alkaline earth metals, and just one of those, right? Because it could be the X2 or the X1. Even though that didn't affect our stoichiometry, it affects what our unknown metal is. If and I don't need to divide by 2. For my data, for the one I have, 137 is like perfectly barium. So I think it's a barium carbonate. If I divide by 2 to say, well, what's the other possibility? I get a molecular weight of 68. And if I divide by 2, it has to be one of my alkali metals. None of my alkali metals have a mass close to 68. The closest thing to 68 would be someplace between zinc and gallium. But those don't have a +1 charge. Gallium has a +3 charge, zinc has a +2 charge. That wouldn't work. So it must be, for my numbers, it must be barium. Very similar to the problem we did last week. I think it was on Mastery Question 12, number 2 or 4, something like that. Are you all still awake? Was that good?
Yeah, I have a quick question.
Sure.
Like, just conceptually, like, why did you subtract the 0.00449 moles?
So that was me just doing the algebra up here, right? I've got this number. My unknown is here. So I'm just going to bring this over to try and get my unknown alone. So
Okay.
that 0.00449, this number, that's this whole thing multiplied together. 0.0712 times 0.1241 divided by 2 gives me that number. And then to get my molecular weight alone, I'm going to subtract this and then multiply, divide to get it across.
Got it. Thank you.
So that was just the algebra. Other questions about this problem before we move on? Okay. Moving on to, wait, the grams of CO2. Oh, does it ask you to find the grams of CO2?
Yeah, it does in the problem.
After we have our molecular weight of carbonate, since that's our limiting reactant, that's I didn't realize it asked for that. Oh, nice. After we've got our grams of carbonate, so here, let me think real quick. Oh, we know our total mass of sample, right? We know that, so after we have the molecular weight of our carbonate, we can calculate the moles of our carbonate, and we can just do that as straight stoichiometry. So, since I know that I had a 1.268 gram sample, I can take my 1.268 gram sample, divide by my molecular weight to get my number of moles of carbonate, and then I know it's a 1-to-1 ratio of moles of metal carbonate to carbon dioxide. And so that moles of metal carbonate is going to be my moles of carbon dioxide. Was that enough, Emmy, or do you want to see the math? Okay. In that case, we'll go ahead and move on to mastery questions set 13, number 4, and number 5. So in these two problems, they're straightforward-ish. There are some really simple mistakes that people make, which make it so you don't get the right answer. But they're very similar to the other problems we've been working on last week and this week. Let's go ahead and read those real quick. Make sure I'm on the right page. Yep, okay. Mastery question number 4. What volume of sodium hydroxide is needed to neutralize a mixture? Oh, this one. Made by mixing the same volume, 10 milliliters, nitric acid, sulfuric acid, and phosphoric acid, if the concentration of each of those acidic solutions is 0.589 molarity. So this is kind of tricky because you're doing 3 chemical reactions. It's very similar to what we just did, except you have 3 chemical reactions, 3 reactants with one thing equal to all of them. And the most common mistake people make is they don't realize that nitric, sulfuric, and phosphoric have 3 different mole ratios associated with them. So I'm going to go ahead and start this problem, number 4, by writing down the 3 chemical reactions. We've got sodium hydroxide 3 times HNO3, H2SO4, H3PO4. And without even putting the products, I can see I've got 1 hydrogen, so I need 1 sodium hydroxide. I've got 2 acidic hydrogens, so I'm going to need 2 sodium hydroxide. I've got 3 acidic hydrogens, so I'm going to need 3 sodium hydroxides. And then, much in the same way we just did carbonates question 2, I can say my moles of sodium hydroxide, because that's what we're trying to figure out, is going to be moles NaOH reacting with HNO3 plus moles NaOH reacting with H2SO4 plus moles NaOH reacting with H3PO4. And for these 3 things, we know the volumes and we know the molarity. So what we're going to do, I'm going to set this up in a kind of how I think about it type way. I'm going to have 0.6, well, let's see. Let's just do this. Molarity, NaOH times volume, NaOH is going to be equal to molarity HNO3 times volume HNO3 times the 1-to-1 mole ratio, plus the molarity H2SO4 times the volume H2SO4 times, with wanting to get it to sodium hydroxide, that's going to be a 2-to-1 ratio, right? Because I want my coefficient, since my end material is in terms of sodium hydroxide, I want my coefficient for sodium hydroxide on top. Plus molarity H3PO4 times volume H3PO4 times 3-to-1 mole ratio. And after we have this kind of conceptual equation set up, we can go through and say, okay, well, which things in this conceptual equation are known and which things in this conceptual equation are not known. We know our molarity of sodium hydroxide, we know the molarity of each acid, we know the volume of each acid. The only thing we don't know is the volume of sodium hydroxide. So if we plug in all of our numbers, at that point it should just be algebra, right? We've done our conceptual chemistry thinking and now we just got to do the maths. So I've got 0.649. Hey, sorry, for my numbers. And I'm going to make it super algebraic, calling my unknown x rather than volume. And this is going to be, all of them for mine are 100 milliliters and 0.5896. So I'm just going to do 0.1 times 0.5896 times 1-to-1 plus 0.1 times 0.5896 times 2-to-1 plus 0.1 times 0.5896 times 3-to-1. And if I give people this equation and I say solve for x, everyone can do it, right? Solve for x, no problem. The important thing here is how we get from the given information conceptually thinking about what reactant we have in common and what that reactant needs to have stoichiometrically balanced in terms of what it's reacting with, the moles times the mole ratio of the reaction. Really kind of same thing we did in the carbonates question. And let me see here. Did that help? I think it was Kylie who asked that one. Okay. And then problem 5. Problem 5 is actually completely different from this. Any questions about this one before I move on? Okay. Making sure no one's typing. Here's one thing I don't like about Zoom is it doesn't tell you if someone's typing. So if someone's typing a question right now, I can't tell. So if you got a question, just put like yes real quick, and then I'll slow down. But I think I waited long enough. So going on to mastery question 13, number 5. This one is kind of like a throwback question to last week. It says, how many hydrogen atoms, oh, this is kind of a throwback question to week 1 almost, maybe week 2. In a 100 milliliter sample of an aqueous ethanol solution, So I'm instantly thinking of how I can make this problem more complicated than I think it's supposed to be. So let me check something real quick. Okay, we've got aqueous ethanol solution. I'm going to make sure I'm not overcomplicating. I'm instantly overcomplicating it in my head, and I want to make sure that it's asking for what I think it's asking for. So this one is interesting. When I first looked at it, I thought it was really straightforward. And now that I'm looking at it, I'm realizing that it's got a trick to it. So, we've got a solution of water and ethanol. So we've got 100 milliliters of 0.9865 molarity ethanol, C2H5. I'm just going to call it C2H6O. And it says how many hydrogen atoms are in the solution. The thing you have to remember is this is a water solution. Water also has hydrogens. So we're going to have to find the number of hydrogens associated with the C2H6O and then the number of hydrogens associated with the H2O as well. So let's do the easy part first, because this is where most people probably jump to. We can find our moles of C2H6, then we can multiply by 6 to get our number of hydrogens from the ethanol. So that's going to be 0.1 times 0.9865. And I'm actually going to do this step separately. Because I'm going to need this number of moles in just a moment. Oh, but I can do that multiplication in my head, thankfully. It's going to be 0.09865 moles C2H6O. I can then convert that into the number of hydrogens associated with that, 0.09865 moles C2H6O times 6 hydrogens 6 moles of hydrogen for every 1 mole C2H6O, using this idea of the atomic ratio. That will get me the moles of hydrogen from the ethanol. It's going to be 0.5919 moles hydrogen. Put little quotes around it. Great. Now, how are we going to get at that idea of the water? What amount of this 100 milliliters is the ethanol? What amount of this 100 milliliters is the water? And that's where that density piece comes in. And as soon as I saw that they gave you density, I was like, oh, they got a trick in mind. So from this, I can say that this is 100 grams of solution. And if I want to get just the water part, I need to subtract off my grams of ethanol, right? My solution is water plus ethanol. And both have a density close to 1. That's why they assume the density is 1. But now, if I want to get just the grams of this due to water, I need to subtract off my grams of ethanol. So I'm going to go 100 grams solution minus 0.09865 moles C2H6O times, got to do some 24 plus 16 plus 6, 46 grams C2H6O for every 1 mole. C2H6O is equal to grams H2O. That's probably the part that tricks people the most. Getting the number of moles of hydrogen due to just the ethanol is fine, but remembering that water also has hydrogens associated with it takes a little bit more thinking, and we have to think about how we can get at that information. Once we kind of get the grams of hydrogen, you're going to do the same process here, where you're going to do grams of hydrogen divided by molecular weight times the atomic ratio. That's going to give you total moles of hydrogen. So you should end up with an equation like this: grams H2O times 1 mole. H2O has 18 grams. H2O times 2 moles hydrogen for every 1 mole H2O. And that's going to give you moles of hydrogen from water. Then you just add those numbers together. That's going to give you your moles. And I think it asks for number of atoms, so you're going to have to use Avogadro's number as well, of course. Did that help? And I think this was Kylie again. Does that make sense? Awesome. Okay. The last part that's kind of interesting is total number of free hydrogens. Yvette, we're just finishing mastery question 13, number 5, and we just did number 4 a moment ago. But we can do it again. It's okay. So the last part here is total number of free hydrogens. And this is really just asking us to identify CH3, CH2OH as how acidic it is, right? Does it give away any H pluses, right? The H2O is going to stay together for the most part. How much does the C2H6O fall apart in water? The answer is not at all. Alcohol groups are not acidic in water. They do not donate H+, so we should get approximately a 0 concentration, a 0 number of free hydrogens in this solution. It's not perfectly 0. We're going to learn about that next quarter when we're looking at acid-base chemistry a little bit more closely, but it's approximately 0. That gets us through, no, we did carbonates question 2, but not carbonates question 1. That gets us through all of those problems, and now we're looking at limiting reactants question 2E. And Yvette, we can go back and do these. I just want to finish this last one. It's a little bit of a long one, but we'll go back to those questions as well. I'll let you look at the board. No, I think it's going to be too confusing since you jumped in partway through this solution. But we can do it again together in just a moment. Let's go ahead and look at what's going on with the limiting reactants question 2E. And Ashley, we can go back and do carbonates question 1 in just a moment as well. Let me add that here. So, this is question 2. So, try one more of these. So we're looking at the reaction of SO2 with O2, sorry, SH2 with O2. We're supposed to predict the products, and then A, B, C, and D. Okay, this is the problem. So this A, B, C, D really has us thinking about it on an atomic scale, and what really throws people off is E just jumps straight to doing a stoichiometry problem, and I feel like there needs to be a little bit more of kind of leading up to what's happening in problem E in step E for this problem, because A, B, C, D all relate to each other, and then part E is like its own separate thing. So it's almost easiest to do E kind of separate from the rest of it. So we're going to go ahead and just do part E separate from the rest of it, getting away from the atomic picture. Okay. So we're looking at, in this problem, we are looking at question 2E. We're looking at SH2 plus O2. Let's see, does it tell us what product to predict? The circle below shows a mixture of dihydrogen sulfide, forms sulfur dioxide and water. So we're going to form SO2 plus H2O. And we have to balance this. So I've got one sulfur, 2 hydrogens. Oh, shoot. Okay, so this is going to get messy quick because I've got an odd number of that. So I'm going to put a 2 there and a 2 there. So that's 4 hydrogens, 2 sulfurs. I'll need a 2 there. So that's 2 sulfurs, 4 hydrogens, 4 hydrogens. And now the oxygens I can do kind of at the end. I've got 2, 4, 6 oxygens, so that's going to be a +3 there. And now I find this step to most easily be done just by thinking about it stoichiometrically. So we are doing this reaction with 38.3 grams here and 30.1 grams of oxygen. That's a G. Okay. So we've got our balanced chemical equation. Following our steps, step 1 is balanced chemical equation. Step 2 is find moles of starting material. Step 3 is identify limiting reactant. Step 4 is subtract and add limiting reactant appropriately. And step 5 is finish the problem. Let's go ahead and start by calculating this. So periodic table's out. Help me out if you've got your periodic table and your calculator handy. Help me out, calculate the moles of O2 or the moles of SH2 just to double check my work. 8.3 divided by 32, 33, 34. 1, 2, 3 moles SH2. And then 30.1. Did anyone calculate the moles of O2? I'm enjoying the awkward silence. Sorry. This is what I miss about the classroom, because in the classroom, I would stand at the front of the room and just kind of look out at everyone awkwardly trying to not make eye contact with me. But in a Zoom meeting, I can't even tell if you're still sitting at the computer or not, because you all have these like squares and pictures. So I can't even tell. But that's okay, we'll just press forward. Did anyone calculate the moles of O2? Is 32 grams per mole, and if we convert 30 divided by 32, we're going to get 0.9406 moles O2. Now in this case, at least with my numbers, I can tell that my oxygen is limiting reactant, and I'm just doing this check in my head. It's not because it's the smallest number. It's because it's a smaller number with a bigger coefficient. So this bigger coefficient tells me I need more oxygen than sulfur. I need about 3:2 ratio. And I've got less oxygen than sulfur dihydrogen sulfide. So I know that this must be a limiting reactant. So in order to calculate, let's see, how many grams of sulfur dioxide would be produced, I'm going to go ahead and do 0.9406 moles O2 times my 2:3 ratio, 2 moles SO2 for 3 moles O2. We can imagine a 0 plus over here because we started with 0 moles there. Important for future chemistry, not important for this class. And then I just have to do 0.9406 times the 2:3 ratio, and that should be it for that problem. The big kind of challenge with this problem, in my opinion, 0.62. The big challenge with this problem, in my opinion, is the way it jumps from D to E it doesn't make it really clear that you're switching from this kind of atomic picture where you're counting like whole numbers to doing moles. And the place where that becomes problematic is it's fine to think about two SH2 molecules with three O2 molecules going to two SO2 molecules. But when we start dealing with these numbers of moles, this is, let me just calculate real quick. This is 6.760 times 10 to the 23rd SH2 molecules. Right? When you get to that kind of scale of moles, it's such a huge number that it's really hard to translate that back to the atomic picture. So that's kind of the tricky part for that one. Did that clear things up? Let me check. Who was that? Did that clear things up for you?
I
Haley?
thought that we had to find the grams of SO2. So then, like,
Oh,
when I did that, I got my moles for the O2 and the H2S, and then I multiplied them by the grams of SO2, and I got that O2 is our what is it? Yeah, so that would be our limiting is O2, and my answer, I put that into the E answer spot, and it said that it was wrong.
did you calculate a number of moles like this using your limiting reactant and your mole ratio?
Yeah.
And then you took this number and you multiplied by the molar mass of SO2?
Yeah.
Okay. I'll take a second look at that. For my answer, I should have gotten something that was about 40 grams. I think yours should be about the same. I'll take a little bit of a closer look at yours. And then we'll move on to the next one. So the question 3, master question 13, number 3 did have a typo yesterday that we fixed. So that should be good now. If you refresh your page and hit generate new change problem values, you should get something that completely works for that problem now. If you haven't already tried the problem, it should work like it just worked right away. Carbonates question 1 is this kind of like student-based problem of, oh no, you spilled acid, what do you do? So in the laboratory setting, whenever we have an acid spill, or even a base spill actually, we use sodium bicarbonate to clean it up. And the question is, do you have enough sodium bicarbonate to clean up your spill? This is stoichiometry with a little bit of logic in terms of what's going to be the limiting reactant. So let me check who asked this one. This is your question, right, Ashley? Okay. So, Ashley, how far through the problem did you make it?
I thought I got to the end of it, but my answer just kept being wrong.
Okay. Let's do it together and see what comes up and see if we find a mistake in the process or if there's another mistake someplace else. So we've got 1.42 molar sulfuric acid. Add some concentrated stuff. And we've got, for my numbers, I've got 89.95 milliliters. I'm just going to go ahead and convert that right away to my liters. Times 0.08995 liters. That should get me my moles of sulfuric acid. And then I've also got, in order to clean that up, I've got 17 grams of sodium bicarbonate. So sodium bicarbonate is NaHCO3. I can go ahead and multiply that by the molecular weight associated with that to find the moles of that I have. Molecular weight for that is 23 plus 60 plus 1, 84. Approximately 1 mole is 84 grams. I can find the moles of each thing. 0.42 times 0.08995 gives me 0.1277 moles of sulfuric acid, and 17 divided by 84 is equal to 0.2023 moles. of sodium carbonate. Sorry, sodium bicarbonate. And clearly, sodium bicarbonate is going to be the limiting reactant because it's the bigger number, but because the mole ratio. So let's look at the balanced chemical reaction for why the bigger number ends up being the limiting reactant in this case. The H2SO4 will react with sodium bicarbonate to go to Na2SO4 plus CO2 plus H2O. In order to balance this out, I'm going to need what did I do wrong here? I'm going to need 2 there to get my 2 sodiums. That's going to give me 3. That's going to give me 4 hydrogens, so I'm going to produce 2 waters in that case. And it's going to give me 2 carbons, so I'm going to make 2 CO2s, and that's 6, and that's 4, 5, 6. Okay, so it's 2 sodium carbonates, 2 carbon dioxides, 2 waters produced, 1 sulfuric acid for that. So this is where we can start to say, okay, well, it turns out the sodium carbonate is going to be limiting. We can tell because, well, there's 3 different ways to kind of do this. My favorite way is to find out the number of reactions you could complete with each. The way I just did it was just kind of like intuitive logic thinking of I need double my sodium carbonate, I need twice as much sodium carbonate, and that number is not twice as big. 0.24 would be twice as big, that's not twice as big. The other way to do it, which I think most students do it this way, is to say, oh, I'm just going to guess and check. And guess and check is actually works, but you might end up wasting your time a little bit. So let's go ahead and just write in what we have for our number of moles, 0.1277, 0.2023. I'm going to say, I think sodium carbonate's my limiting reactant, so I'm going to do minus, I'm going to have 0.1277 moles H2SO4 minus 0.2023 moles NaHCO3 times 1 mole, 2 moles. Wait, let me get my mole ratio right here. I'm going to mess it up. No, I was right the first time. 1 mole H2SO4 for every 2 moles NaHCO3. And this is why I have to be careful and make sure I write down my units properly, because this way I can see what cancels, and I'm going to get sulfuric acid minus sulfuric acid with bicarbonate canceling out. When I do this, I'm going to get my amount of excess sulfuric acid, 0.1277 minus, let's do this, 0.2023 divided by 2 minus 0.2077. I'm going to get 0.02655 moles excess. Sulfuric acid. So first answer is no, this is not enough carbonate to clean up the sulfuric acid. And then if the answer is no, we want to say how much more sodium carbonate do we need to clean up the sulfuric acid? And if the answer was yes, we want to know how much excess sodium carbonate we had. For the numbers we had, the answer was no, it's not enough. So I want to find out how much more sodium carbonate I need to react with this amount. And there's 2 ways we could have thought about it. It's most reasonable because it's asking for how many more grams. So I'm going to take this moles of excess and figure out how much sodium carbonate it takes to react with that excess. I'm also going to switch the math to the way I like to do it, which is going to be minus 0.2023 times a 1 to 2 minus 0.2023. That's going to give us the 0.02655. That's going to give us 0. I like to do my math in columns because it lines things up nicely rather than in the long way. The long way allows for unit analysis much better. So if you are first learning stoichiometry, I would do it the long way, but after you practice some, the column way is really nice. So now I'm going to figure out how much sodium carbonate it takes to react with this leftover acid. Am I off a 0? Nope, I'm good. Okay. So I'm going to do 0.02655 moles H2SO4 times mole ratio, 2 moles NaHCO3 for every 1 mole H2SO4. That will give me my moles of sodium carbonate, sodium bicarbonate that I need to finish reacting. And then I can multiply by the molecular weight of sodium bicarbonate, 84 grams per mole. And that should get me how much more sodium bicarbonate I need in order to finish neutralizing that acid spill. Important thing, as Ashley just pointed out in chat, make sure you do it for sodium bicarbonate, not sodium carbonate. Hopefully that problem works out for you.